Hello, my name is Wyatt Olea.
And my name is Saurabh.
I'm Babananda Kini.
My name is Hiuru.
I'm Sandeep.
And for our graduate project, we decided to perform a mechanical analysis of test specimens that were 3D printed from wood filament. All of the most basic 3D printers on the market today can at least print with ABS or PLA filament. The more advanced 3D printers can support even more kinds of filament. For those hobbyists with sufficiently advanced 3D printers, there are quite a few filaments to choose from. Among those filaments is a type called wood filament. It is made of 40% sawdust and 60% PLA bonding agent. As you can see here, wood filament has these four characteristics. It has a high-quality wood texture, so you can print objects that look and feel like they are made of wood. It's non-toxic and has no smell, so it's safe to print and environmentally friendly. It has low shrinkage and good toughness, meaning that it is easy to design for, and any object made from it will be fairly sturdy. It also has a printing temperature between 190 and 200 degrees Celsius. This means it has a low processing temperature. The shade of the extruded filament can be changed by altering the print temperature. Our school has several testing labs on campus that can perform a variety of tests. Some of those tests include tension tests, compression tests, and torsion tests. For our project, we performed compression and tension tests on specimens that were 3D printed from this wood filament. We hope that our research can be useful to a variety of people. For example, additive manufacturing is currently used to make simple homes. If someone wanted to use wood filament in their design, they would need to know the mechanical properties of objects that were 3D printed from wood filament. Our research could help them. Likewise, there are many hobbyists with 3D printers who have access to wood filament as well, and they too may find our findings useful.
Talking about the experimental methods used for this analysis, we consider two kinds of mechanical behavior. How the filament would behave in the case of compression testing and in the case of tension testing. In the case of compression testing, we used an equipment which was an electromechanical equipment, and this make was Mark 10 ESM 1500. The picture of this equipment is on the left of your slide. To find and analyze the material, we used a load cell of 2500 newtons capacity, and it had a load cell resolution of 2 newtons. This helped in determining minor changes during the application of compressive forces. It had a strain rate of 0.001 second inverse. The make of the camera to capture the activity was ACA 640, and it had a resolution of 750 micrometers. In this particular experiment, the software Aramis was used to perform and comprehend the digital image correlation testing. Aramis digital image correlation software is an optical analysis tool that uses the evaluation of sequential digital images for measurements of deformation, strain, and displacement. The same software was used for tension testing too. In the case of tension testing, a servo-hydraulic testing equipment was used. The make of the machine was MTS. In this case, we slightly differ from the compression testing A load cell of 25,000 Newton capacity was used. It had a larger resolution as compared to the compression testing. The load cell in this case had a larger resolution of 5 newtons. Hydraulic grips were used to hold the test specimens while the tensile forces were applied. The camera that was used to perform the DIC, or the digital image correlation, was the same as in the case of compression testing, which was ACA 640.
There are two different test specimens that we made. There are the tension test specimen and the compression test specimen. At first, we have only planned on testing specimens made from wood filament. But then, we decided to test specimens made from PLA filament as well. Now, we want to do this because wood filament is made about 16% PLA and 14% sawdust. And we want to see how they would compare.
To confirm the consistency of our tension tests, 6 testing specimens were subjected to tension testing. 3 of the specimens were made from wood filament, and the other 3 were made from PLA filament. The data collected from these tests was plotted in a single stress-strain plot. To help differentiate between the test specimens, the data in our plot was color-coded. The green lines indicate specimens made from wood filament, and the red lines indicate specimens made from PLA filament. The consistency of our compression tests was confirmed by subjecting 5 testing specimens to compression testing. 2 of the compression specimens were made from wood filament, and the remaining 3 were made from PLA filament. It should be noted that many, but not all, of the samples were tested to failure during the tension and compression tests. The testing specimens that were made from PLA filament were tested until failure for both tension and compression. However, the testing specimens made from wood filament were only tested to failure for tension. During the compression tests, the specimens made from wood filament were only tested until yield. It should also be noted that the average width and depth of the dog bone test specimens made of wood filament were different from the dog bones made from PLA filament. The average width and depth of a dog bone made from wood filament is about 6.37 millimeters and 6.06 millimeters respectively. The average width and depth of a dog bone made from PLA filament is 6.07 millimeters and 6.15 millimeters respectively. Both sets of dog bones were printed using the same G code, so it is unclear why their dimensions are slightly off. Because these testing specimens have different average cross-sections, the results of the tension tests may be affected.
The stress strain curve of every sample in both tension and compression shows the characteristics of a brittle material. Because brittle materials do not have a yield point and don't strength harden, the ultimate strength and breaking strength are the same. Brittle materials also tend to fail during elastic deformation and don't show any plastic deformation at all. This results in a stress-strain plot of a curve that approaches a horizontal asymptote, but fails before exceeding a certain stress and strain. The stress-strain curves plotted from our tension and compression test data share the same characteristic shape. Before the test data was even analyzed, we could tell that the test specimens were fairly brittle by examining their fracture pieces. As brittle materials tend to fail before plastic deformation occurs, testing specimens subjected to tension do not experience the necking, which is common before failure in ductile materials. This means that the brittle fractures are very even, and a reassembled testing specimen would look the same as the original because there wouldn't be any necking on the cross section. All of the tension specimens for both wood and PLA failed in a manner consistent with a brittle fracture. Analysis of the test data and the test specimens indicate that wood filament and PLA filament are both brittle materials. As wood filament is about 40% sawdust and 60% PLA base, it makes sense that it would share the characteristics of a regular PLA filament. The fact that PLA seems to reach a higher stress value than wood filament is therefore a result of the difference in composition between the two filaments.
Materials play a dominant role in additive manufacture, particularly when considering materials for engineering structure applications. Mechanical properties of materials are surveyed, including compression strength and tensile strength. Mechanical behavior of two filaments, wood filament and PLA filament fabricated with layered method of additive manufacture was measured, and compared to each other, the tensile deformation behavior of wood dogbone and PLA dogbone was limited by inherent brittle mechanism, resulting in strain to failure value of 10 to 20%. In contrast, there is no change in the brittle behavior of the both specimen materials in the tensile test result as well as in fracture type. On compression test, the specimen shows higher failure strength of value 35 and 45 MPa for wood and PLA specimen respectively. But the results found very inconsistent among the three specimens. Both the materials again show the brittle behaviors and under compression loading. Stop. Thanks for your attention, and thanks the teaching assistants kind help and the related reference for this project.